The first way we're going to solve for a differential equation is the old-fashioned way we did in calculus, is separation of variables. Okay, so separate equations basically is we have an equation that you can separate using the differential equations, differential variables situation. If you don't remember how that is, it's pretty straightforward. We'll get a nice little review how this is going about, but this is the easiest of the alternative ways we're going to deal with in this one, in the situation itself. Okay, so basically, given this situation of a differential equation, is when we have two different functions in terms of x and y, and again we have our independent variables here, is basically just cross multiply, if you remember. Bring this to the outside, and then bring this to the other side itself, and now we only have one side of the equation of one variable, and the other side of just another variable. So in other words, just doing that gives us this. And now we just take the integral of both sides individually, and that's how we solve for it itself. So in other words, we're going to have this as our answer, right? Because since we're integrating, we have our constant c, we don't really know how to solve yet. But we do have a little bit of fun with it anyways, and we have some painful one at the very end. Okay? So let's try this out. So we have a here. And again, if you notice, this is a nice easy one. Again, just cross multiplying. So multiplying this way, multiplying that way, gives us y squared dy is equal to x minus 5 dx. Okay. So now we just take the integral of both sides with respect to its respective variable. So now there is no implicit here, so we're not worried yet. So no double integration like it was in multivariable calculus. Okay. So integrating this gives you x to the third over 3 plus c, and on this side we get x squared over 2 minus 5x plus, let's call this d. Okay. Now it really doesn't matter if I subtract the c. It's a constant minus a constant, so it's pretty much obsolete. So we can actually rewrite it like this. And just it gets engulfed in some arbitrary c value. And now if you notice, it's very similar to what we exactly have now. Okay. Now the last step is to solve for the original equation. In other words, just solve for y itself. So I don't want y cubed, I just want y. So multiply everything by 3. And again, a constant times 3 just gets engulfed to just a single constant. Nothing really happens there. And then finally taking the cube root of both sides. And now we're done. Alright, so now let's try one when we actually have an initial condition. Alright, so very similar. We'll again cross multiply. Or actually, do we have to? Kind of cross multiply. Ish. Right, we're going to bring this to this side and then divide this over, actually. So we have 1 over y minus 1 dy. And the other side will also have 1 over x plus 3 dx. So now we take the integral both sides. And this is going to be a little bit of a trend going forward, is if you don't remember, just a quick little note, integral of 1 over x is ln of x. So that's exactly what we have to do here. The only difference is technically it's a u substitution, but it's natural log. But u equal that, and then our derivative is just going to be 1. And same thing applies here. So in either case, it's going to be ln of u, ln of w, and then we would just replace what was u and w to begin with. So we get this. Okay. So now we do what we did here, is solving for y. So again, going back to a little bit of pre-calculus. So to get rid of the ln's, we have to just take it to the e power, or like that. Well, it's a bad e, but just e power. So these cancel, so we just get y minus 1 on this side. However, this is all raised to it, so you just have e to this whole power there. Okay. Now again, a little bit of pre-cal and knowing exponential rules. This is the same as running like this. Because technically we multiply your adding powers together. But again, this is just some constant, right? E to the some value is just a constant. So really, again, if you want, you just multiply by a constant. So all of that simplification ends up looking like this. All right, so last step, adding the 1 over. And there we go. Now we're at this point here. Okay. And then now the last step is using our initial condition. So when x is -1, the y value is 0. So 0 is equal to, well, x is -1, so we c to the e to the natural log of, plug in -1, so that gives you 2 plus 1. Okay. Well, best part is these cancel. So these cancel. We just get 2 plus 1. And then we just solve for c, so subtract the 1 over, and then just divide by 2. We find out c is equal to -1/2. So therefore, my answer, or the function that works, that makes this the solves for this differential equation, and it's the exact one, unlike this one, right? This is just a family of it. The exact one is y equals -1/2 e to the natural log of x plus 3, and then plus 1. Now, you can't write it like this. Remember, I noticed you just cancel. But, we're not going to go too crazy when it comes to the algebraic. I want to be that picky about it, but technically, you could just leave it like this. That's the definition, or, leave it like that. That's the actual simplified version. But, they are technically equivalent of each other, so it's nothing too crazy to deal with. Okay. And now let's try C. Okay, so this looks like a horrible mess you may look like, but it's actually not as bad as you may think. So we're going to multiply this on that side and then multiply that on that side. So we get all the bottom, so it's cosine of y plus e to the y dy. And on the other side we get 6x to the 5th minus 2x plus 1 dx. And now we just integrate both sides. All right, so integral of cosine is positive sine. This is just itself. This gives me x to the 6th minus x squared plus x plus c. And as of now, we cannot technically solve for y, so we'll just leave it like that for now, I just say.